In this video, we're going to learn about a new carbon-to-carbon bond-forming reaction. So those are always monumental reactions because organic chemistry is the chemistry of carbon. And when you can start connecting different carbon chains, you can create new shapes, and those are like new ridges on a key that will unlock doors of possibility. Now, let's get a bird's eye view of this thing. It's called the Wittig reaction. And this was the last name of a German scientist, and so the W is pronounced like a V, so the Wittig reaction. All right, what does it look like? Well, you'd have some sort of an aldehyde or a ketone, and you treat it with this really weird looking thing. You've got some type of a carbon chain. The carbon has a full negative charge, and the phosphorus, it's bonded to a phosphorus that has a full positive charge right next door, and there are 3 benzene rings attached to that phosphorus. Now remember, when benzene is a branch, when a benzene ring is a branch, when a benzene ring is a branch, it's called a phenyl branch. And that pH there is what these pHs here are coming from. So those are all just 3 benzene rings acting as a branch off of that phosphorus. All right, well, what's that going to do? That mystery molecule, excuse me, whatever carbon you have bonded to that phosphorus, that carbon ends up replacing the oxygen. So you still get that double bond there, but now the double bond is going to whatever carbon was bonded to that phosphorus. And that's it. That's the overall reaction. All right. So at this point, that should look like black magic. So why isn't that black magic? How is this reaction happening? Well, it all starts with an SN2 reaction. Those beautiful substitution reactions you learned about in Organic Chemistry 1. You'll have an alkyl halide, for example. The first thing we have to do is make this weird contraption in the middle. And we'll talk about what that is, but we have to make that first. And we make that by doing an SN2 reaction. We're going to take that carbon, that's the carbon we want, and we're going to treat it. It has to have a leaving group on it. Now notice, we're going to do an SN2 reaction to form this phosphorus-containing carbon compound. And so the restrictions of an SN2 reaction apply. The carbon can be primary or secondary, but it cannot be tertiary. It cannot be bonded to 3 other carbons. In that case, this would be too crowded, and the nucleophile wouldn't be able to come in. Our nucleophile is our triphenylphosphine. That's what that's called. 3 benzene rings bonded to a phosphorus. So phosphorus is just underneath nitrogen on the periodic table. So it has 5, it's in group 5A, it has 5 valence electrons, 1, 2, 3, 4, 5. So you can see it's going to have, just like nitrogen, it's going to have 1 lone pair and 3 bonds. Well, if each of those bonds is to a benzene ring, remember benzene as a branch is named as a phenyl ring. In that case, this is called triphenylphosphine. Now that actually looks, now if you want to see another 2-dimensional picture of that, you could see it here. Looks a little bit like that, right? Kind of like my beautiful drawing. And then, if you want to see what that looks like maybe as a 3D model, it looks a little bit like this. And finally, if you zoom out to our macroscopic level, what it looks like to us on an enormous scale is just this white solid there. So that's triphenylphosphine. And so you need that as this reagent in this reaction. That phosphorus ends up acting as a nucleophile. It's more electronegative than the carbon, so it pulls electrons to itself. Also, it has this lone pair, and so those are going to attack your electrophile. Now, bromine is electronegative, steals electrons to itself, and makes the carbon become slightly positive. So the phosphorus, with a slight negative charge, is going to attack that carbon from the back and kick the bromine off. So this is a classic SN2 reaction. So start a nucleophile, looks a little crazy. Well, after that happens, the key thing that you really need to remember, we're going to use this later, is you form this phosphorus compound through an SN2 reaction. And so this carbon cannot be tertiary. That carbon cannot be bonded to 3 other carbons. That's what it means to be tertiary. Cannot. Because in that case, it's too crowded, and the phosphorus would not be able to come in and attack it. Okay, well, once we have that, we're pretty close to having that weird phosphorus compound that we wanted in this recipe. We have the carbon that we wanted. We have 3 hydrogens. Those are the 3 hydrogens we have here. And we do have the phosphorus now bonded to 3 phenyl rings. So capital P, lowercase h. So this is 1 phenyl ring, another phenyl ring, a 3rd phenyl ring. Instead of drawing out those 3 6-membered rings, I'm just going to abbreviate them with this pH, and that's standard practice. Okay, well, the phosphorus has 4 bonds, and so just like when nitrogen has 4 bonds, it gets a full positive charge. So you can see that we've already formed this. Now, just for the negative charge on the carbon, we need to rip an H plus off of there. So we need that to don't act as an acid, right? Acids donate H pluses. And how can we get this to act like an acid? Because right now, it's not looking like an acid. We have to add a very, very, very strong base. And a very strong base is something called butyl lithium. And you see a metal, and instantly you should be like, that's going to make a carbon nucleophile. Just like with Grignard reagents, metals have such low electronegativity, they give their electrons away to whatever they're bonded to. And here we have a butyl carbon chain, so 1, 2, 3, 4. And so if you have butyl lithium, this last carbon sort of has a full negative charge, and the lithium is there to stabilize that. Right, lithium gives its electrons away to that carbon, so that's butyl lithium, Buli, and that acts as a really strong base. This is so intense that it just steals this hydrogen, and the electrons go onto the oxygen. So what we end up with there was that strange phosphorus molecule that we had above. Right, that bond becomes a lone pair, so now we have that lone pair, and that carbon has a full negative charge. So that's the compound we had up here, carbon with a full negative charge in the lone pair, right next to a phosphorus with a full positive charge. Now this strange thing that we're going to use, this is called an ylide. An ylide. An ylide is a compound that has a carbon with a negative charge right next door to a heteroatom, it's an atom different from carbon, with a full positive charge right next door. Okay, now, you may remember from Organic Chemistry 1 that if you have a lone pair next to a positive charge, that gives rise to another resonance structure. So sometimes the ylide is drawn like that. Sometimes, though, it's drawn as the other resonance structure. To get the other resonance structure, all we have to do is put that lone pair going toward the positive charge. And so you'd have the same thing, but really, in this other structure, you'd have that another pi bond there. And so that takes care of the charges. Now, some people, you may look at this and you may say, oh, well, that's the better resonance structure. After all, this has no charges, this has opposite charges right next door to each other. However, if you think about this pi bond, the second bond there, remember, pi bonds form when you have parallel p orbitals. But carbon is in row 2 of the periodic table, and phosphorus is in row 3. That means phosphorus is much, much bigger. So the p orbital on carbon is going to be tiny, tiny, and then phosphorus is going to be enormous. And so the overlap is really not that great. You have a tiny bit of overlap, but the truth is the overlap is not that great. You really don't get a full pi bond. The electrons end up really just being stuck on that carbon, the one that lost its hydrogen. So some people draw it with that double bond. If you see that, don't get scared. It really is the same molecule. But the truth is that this structure on the left is the dominant one because the p orbitals don't overlap well enough to form a real pi bond. And actually, when we draw the mechanism in a second, you'll see that it's actually this structure on the left that really is involved in the mechanism. Okay, so let's say, now remember, what we had was some sort of a ketone. In order to form our ylide, we needed to do an SN2 reaction with whatever carbon chain we needed, just with triphenylphosphine. That gives us our ylide. But once we have our ylide, it's going to react with this ketone to get our product. So let's see how that looks. How does that react? Okay, well, let's say we have acetone, simplest ketone that you can have, and this phosphorus ylide comes by. Okay, well, what ends up happening here, in this case, is this carbon in the carbonyl ends up sort of, which is slightly positive, right, ends up aligning with the negative carbon. And the oxygen, which is slightly negative, aligns with the positive phosphorus. So you can see these opposite charges are helping to align these molecules. And you end up doing a 2-2 cyclic addition. Oops. So remember that when you do these cycloadditions and you're classifying them, you give the numbers in there in that brackets. Those tell you how many atoms are in between the two bonds you're forming. So we're going to have 2 on one side and 2 on another, and we're going to form bonds between those two. So this pi bond ends up attacking the positive phosphorus. Oops. And the negative carbon ends up attacking the carbonyl carbon, and that all happens in one step. So that's crazy. Now I should say, you guys aren't responsible for drawing this particular mechanism. I just want you to see once what it looks like. Now what you get after that step is you end up getting this oxygen now bonded to the phosphorus, this carbonyl carbon now bonded to the other carbon, and these have a single bond. We have our hydrogens here, and this phosphorus has 3 phenyl groups on it, 3 of those benzene rings acting as branches, and a full positive charge. Now, let's not worry about the full positive charge right now. That species breaks apart and crumbles and fragments really quickly. What ends up happening is the sigma bond to the oxygen goes toward the phosphorus, and the single bond between the carbon and the phosphorus goes toward the carbonyl carbon. And so you can see you're going to form a pi bond, a second bond between those two carbons, so that you end up with a carbon with 2 hydrogens double bonded to your what used to be the 2 carbons, the carbons of the acetone. Now you also end up with this phosphorus compound with 3 phenyl rings, a double bond to an oxygen. That's going to go off and live its own life, but notice the end result of this phosphorus ylide reacting with the ketone is that the oxygen is replaced by the carbon in the ylide. That's the important thing you need to remember for synthesis. And that carbon in the ylide can only be created through an SN2 mechanism. Okay. All right, well, that is the Wittig reaction. You take a aldehyde or a ketone, you react it with a phosphorus ylide, and whatever the carbon is in that ylide that replaces the oxygen in the aldehyde or the ketone, you end up forming a new carbon-to-carbon bond. Not only that, but it's a carbon-to-carbon pi bond, which is rich in chemistry. You can do all those addition reactions that you learned in Organic Chemistry 1 with that beautiful pi bond there. So in exercise 2037, what they're asking you to do is to create these alkenes. And now when you see alkenes, you should think, I could make that with a Wittig reaction. Now, what reagents do you need to use? Okay, well, there are two possibilities. Put sort of a line through the double bond and draw the two sides separately. So draw the ring and draw the, in this case, the two carbons on the right. So we have the ring on the left and the two carbons on the right. And we used to have that double bond in between. Okay, so we're going to think about these separately. Now, we have two scenarios. Either you could have the ketone on the ring, and one of these carbons here can be bonded to a phosphorus, a triphenylphosphine. That's one possibility. Or the ketone can be on the carbon and the ring could be bonded to the triphenylphosphine. Oops. Right. Now I'm drawing it here with the double bond. You could just as well draw the ylid version of it with the positive and negative charge right next to each other. Both are correct. And now you want to think about which one of these is better, because theoretically at first view you might think, well, they both would work. However, remember that the phosphorus compound is made through an SN2 reaction. And in this molecule on the right, the carbon that you would do the SN2 reaction on is primary. Oops. It's primary. It's only bonded to one other carbon. Whereas that's on the left. In the other molecule, the carbon that has the triphenylphosphine on it is secondary. It's bonded to two other carbons. Well, what's better for an SN2 reaction? The less crowded position. And so it's going to be easier to make the phosphorus ylid on the left than it is on the right. And so the reagents you want to use to make this are going to be those reagents on the left and not those on the right. These may even work, they just won't work as well as the ones on the left. Okay, well, how about B? How would that work? What reagents would you need to make that happen? Well, first, draw a line through the double bond and draw each of the pieces on each side of that. So we've got this six-membered ring, and then carbon, and on the other side we just have one carbon, right? This one carbon there. So let's draw those twice because we have two possibilities. In one of them, where the double bond was, I'm going to have a double bond to the oxygen. That's one possibility. And in that case, the other thing, the carbon, would be double bonded to the triphenylphosphine. And just to fill this out, this needs two more hydrogens. So that's one possibility. The other possibility is that the carbon all by itself has the double bond to the oxygen, in which case you have formaldehyde, the simplest aldehyde. And in that case, the carbon with the ring would be double bonded to the triphenylphosphine. So these are your two possibilities. Now you want to consider the carbon bonded to the triphenylphosphine. Which one of these is better? Well, this carbon on the left is bonded to no other carbons. The carbon on the right that's bonded to the triphenylphosphine is bonded to one other carbon. You want to use the one that is less crowded, because that is going to be easier to do the it'll be easier to do the SN2 reaction that forms the ylid on the less crowded carbon. And so this structure here on the left, that's the better recipe for making this Wittig reagent, for doing this Wittig reaction. The one on the right probably would work. I mean, you could definitely do an SN2 reaction on a carbon that is primary, like this one is here, but it won't be as fast as if the carbon has no carbons on it at all. Okay, let's go through that same procedure for C. We have this alkene, and now when you see alkenes, you're like, how can I make that? I know, I can do a Wittig reaction. So you put a line through the double bond, and you draw each of the pieces on both sides. So we have a carbon just there on the right. Now I'm going to draw those twice because we have two possibilities. Either the ketone is on the left, the double bond to the oxygen is where the double bond was going in the original molecule, and the double bond in the other carbon will go to a triphenylphosphine, or the ketone is on the carbon, or in this case the aldehyde, is the double bond to the oxygen is on the carbon that's all by itself, and the other one has a double bond to the triphenylphosphine. So notice, when you do this, you're keeping that double bond, but you're doing it separately on one molecule and on another. And those double bonds are either going to be to an oxygen or to a triphenylphosphine. So these are your two possibilities. And you want to think about which one has the triphenylphosphine that's easier, which one has the ylide that's easier to form. To judge that, look at the carbon bonded to the triphenylphosphine and ask how many other carbons is it bonded to. This one is bonded to 0. So again, look at the carbon bonded to the carbon bonded to the triphenylphosphine. Ask yourself, how many carbons is that bonded to? 2. Well, 2 carbons is more crowded than 0. And so it's going to be easier to form this ylide with an SN2 reaction because there's less crowding. The nucleophile can come, swoop in, and attack much more easily. And so this is the more efficient Wittig reagent. All right, we've got D. You see an alkene, and now your creative mind thinks, I can create that with a Wittig reaction. So you draw a line through the double bond, and you draw both of the pieces on either side of that double bond separately. So those pieces. You just have the double bond in between them normally, but now we're drawing them separately. So those are our pieces. You want to draw them twice because you can have two possibilities. So redraw the double bond on each of the molecules. So double bond, double bond, double bond, double bond. But in one, put the oxygen on one half of the molecule and the triphenylphosphine on the other double bond, so phosphorus with 3 phenyl rings, benzene rings that are acting as branches, and in the other, do the opposite. So if I put the oxygen on this branched thing, I'm going to put the oxygen on the non-branched thing on the other one, and the first will get the triphenylphosphine. Okay, now look at the carbon bonded to the phosphorus and ask yourself, how many other carbons is that bonded to? Here, 1. Look at the carbon bonded to the phosphorus. How many other carbons is that bonded to? Here, 2. 1 is less crowded. That means it's going to be easier to do an SN2 reaction on this less crowded carbon. The nucleophile will be able to swoop in and attack the electrophile more easily. And so this is that will give you the more efficient Wittig reagent. All right, last one for this. We have E. So first step, crack that bond in half, redraw the two pieces separately. So we've got a benzene ring bonded to a carbon, and then on the other side it looks like we have this cyclohexane. Okay, well, and you want to draw that twice actually because you have two possibilities. Okay, well, where you had the double bond, put the double bond again on both of your pieces. But in one of them, put the oxygen, and in the other, the triphenylphosphine. So the phosphorus with 3 benzene rings, those pHs. On the other, do the opposite. The oxygen goes on the opposite molecule, and the triphenylphosphine goes on the opposite molecule. Now these are your two possible Wittig reagents. Okay, next, look at the carbon that's bonded to the phosphorus. Ask yourself, how many carbons is that bonded to? Here, 2. How about on the right? Look at the carbon bonded to the phosphorus. How many carbons is it bonded to? Here, 1. Well, 1 carbon, that's less crowded. That means that the phosphorus is going to be able to swoop in here as a nucleophile and attack that carbon more easily to form the ylide. And so it'll be easier to form these Wittig reagents than it will be to do the other ones, because you can do that SN2 reaction here more easily. So hopefully that gives you a sense of how to do these Wittig reactions. Wittig reaction, like the Grignard reaction, like the Diels-Alder reaction, is really profound because it allows you to form new carbon-to-carbon bonds. The overall change that you're making is you're turning the oxygen in an aldehyde or ketone into another carbon. So you're forming a carbon-to-carbon pi bond. And so when you think of it in the forward direction, anytime you see a ketone or an aldehyde, think, I could turn that into a carbon if I wanted to. And in the reverse direction, anytime you see an alkene, think, I could make that if all I had was a ketone. And it happens, and the one thing you want to remember is that because the triphenylphosphine, when you form the ylide, you'd form it through an SN2 reaction, you always want the phosphorus to be on the least substituted carbon possible. Otherwise, there's not going to be room here for that phosphorus to attack as a nucleophile. And that is planning an alkene synthesis with a